I'm glad to hear a chuckle from that, because that took me like a good 20 minutes the other day. Before I start, I just want to say how inspirational it is for me to be a part of this symposium. And I want to thank David and Marjorie for inviting me. Recently at the University of Idaho, we were thinking about better ways to structure our graduate training program. And one of the ideas we had was really inspired by all of you who are part of this symposium and other people that I see in the room too. And the idea was to try to create the naturalists of tomorrow. And these are people who are as competent with a laptop as a pair of binoculars, can spend the morning capturing organisms in the field and the afternoon writing R code. And you guys really exemplify the best of that, and I really admire you all. So thanks. By contrast, I'm like when they pulled Dusty Keith Richards out of the closet to perform at the Rock and Roll Hall of Fame induction ceremony, but I'm still happy to be here. Okay, so in the movie Terminator 3, no, just kidding, I'm not going to care. I don't have time. I'm going to talk to you a little bit about the processes that structure communities. I was thinking about this last year when I was on vacation. These are my two kids here, so just the gratuitous dad photo up here. But here they are on the big island of Hawaii, and the whole time that we were on the big island on a family holiday, I was obsessed with thinking about these processes of ecology and evolution that work together to structure our communities. And I think you'll see immediately how this connects to ideas that have come in the two talks that preceded me. If we start to think about community assembly from first principles, we can identify a number of different processes that might be involved in that community assembly. For example, things like genetic drift affecting trait evolution within species, community drift affecting the balance of species in communities, biogeography, so transitions among lineages, among regions, natural selection, habitat filtering, speciation, and so on. And this list isn't exhaustive. This is just the things that first come to mind for me when I'm thinking about how communities are assembled. One of the problems that I think that we're facing now in our field when we try to integrate data together and use methods to understand empirical patterns is that these methods, in a way, live on little methodological islands. So, for example, the distinction between community drift and habitat filtering lives on an island called phylogenetic community ecology, metaphorically. Genetic drift and natural selection in the macroevolutionary world is typically dealt with through comparative methods. Biogeography and speciation are dealt with through historical biogeography. And one of the things that I would really like to be able to do, but can't completely figure out how to do, is to take a more unified view of all of these processes and how they might predict patterns that we see in the natural world. I've tried to approach this for years by using statistical model-based approaches. So the idea there is that you develop a model that's analytically tractable. With that model, you can calculate a likelihood, and with that likelihood, you can build a maximum likelihood or a Bayesian MCMC method to try to infer model parameters or do model selection. I've been resistant to other things that are not that for a long time. But the young naturalists of tomorrow, tomorrow's naturalists that we already have at the University of Idaho have recently been pushing on that and pushing back a little bit and have convinced me of the utility of machine learning to try to solve these problems. If because of that robots in the future come to try to assassinate me, I'm going to be super mad. But in the meantime, I'm going to tell you about a couple forays into machine learning approaches that we've made in this area. And I think they do relate really well to this theme of species interactions and macroevolution because they deal with macroevolutionary scale phenomena, and you can directly compare models that have species interactions with models that don't. Those of you who know me well know that I much prefer to talk about other people's work than my own, and then I like to advertise for those people, so I'm going to do that today. And there are two subjects of that advertisement. The first is Megan Ruffley. She's a PhD student at the University of Idaho. She's my favorite kind of PhD student to work with lately, which are PhD students who are not in my lab, but are in other people's labs, because then other people do all the paperwork and I just get to do the fun stuff. So, Megan is a PhD student in Dave Tank and Jack Sullivan's lab, and if you ever see this name coming through your university application system for a postdoc or faculty position, you should definitely hire her. Megan has developed a method called CAMI, which stands for Community Assembly Model Inference. There's a GitHub that you can already visit. The paper is in press at Ecology and Evolution, so you'll be able to get it soon, and if you want it sooner than soon, then just email me and we'll send it to you. The idea behind CAMI is to deal with the questions posed in phylogenetic community ecology in a slightly different way. So in phylogenetic community ecology, we're trying to figure out how we go from a regional pool of species to a local community. The structure that we built in CAMI is we can simulate a phylogenetic tree under something like a birth-death model. And when we do that, we can also simulate species traits on that tree, so the traits are going to be important in the process of community assembly. So here's just an example of a fake trait evolved on a phylogenetic tree. We can then consider those species that arise from that joint birth, death, and trait evolution process as our regional species pool. And we can assemble those species from the regional species pool into the local community through processes of dispersal. And then, if we want, we can determine who gets to stay in the local community by the species traits. This, I think, is really consistent with the way that people have always kind of described the community assembly process. And it's the conceptual framework, at least, that I think lives behind normal phylogenetic community ecology methods. In order to use species traits to determine who gets into the community, we have a couple of cartoon versions of how those traits might matter. One is habitat filtering, so here's a plot of our habitat filtering model. We have a probability along the y-axis, the trait along the x-axis. And you can see that there's some optimal value, and if a species trait is close to that optimal value, they have a really good chance of making it into the local community, and it decreases as they get farther away. We use the exact mirror of that for competitive exclusion, so here there's a trait, but in this case, the valley in our surface here represents a trait that's too similar to species that are already in the local community, and so they have a low probability of being able to coexist with those species, and as we get more and more distinct, we have a higher chance of getting in. Again, this I think is consistent with the verbal models of community assembly that people have in phylogenetic community ecology. The main difference for CAMI is the methodological approach. So in traditional phylogenetic community ecology, we use things like placement of the species on the phylogenetic tree, and in the local communities measure over-dispersion or clustering on that tree and try to make inferences about process. I would like to be able to write down a likelihood for this model, but I can't because I'm not good at math. So Megan's idea was, what if we just simulate this whole process that I just described, including evolving a regional community of species and then assembling a local community many times. And then we use the simulations to fit the model to data, but instead of using likelihood, we use a set of summary statistics. And Megan has been able to carry this method out using two different methods based on summary statistics. One is ABC. That was my suggestion because I'm trying to get back to my old world of maximum likelihood and normal Bayesian inference as best I can. And then Megan said, well, let me just try random forest too because it's fast and easy and we'll just see what happens. And I said, don't do that. She said, I already did. Okay, so this is the exciting thing I think about this type of approach is that the intellectual work, I think the real magic here, the sort of magic Harry Potter spell words that you use to make this stuff work are in the choice of the summary statistics. And this is where there's like a sort of an art to knowing enough natural history and statistics to picking, wisely choosing the summary statistics that will give you the things that you want. So manganese aspects of the tree, like tree balance, branch lengths, spectral density, breakdowns from Helen, Morlon, and so on. Aspects of the species traits, like their mean, their variance, and their skew. And then, critically, aspects of the traits and tree together. Phylogenetic signal, where the species are on the tree, what traits they have, all combined into a certain sum of statistics. I don't have time to go into detail about this, but I'm happy to tell you more about the way that we've approached this, if you ask me later. And I think that if you read the papers that are frustrated with current approaches in phylogenetic community ecology, many of them suggest that it's the information about the tree and the traits together that somehow are going to tell us the right answer. And I think that this Megan's work proves that that's correct. So here's a plot of how well this method works. This slide's a little bit busy, but let me walk you through it. Here we have the error rate for classifying 3 different models in phylogenetic community ecology: habitat filtering, neutral, and competition. I know that's cartoonish, and probably most people who work on real organisms think that both of those things are happening, but still, it's a good starting point. The top 2 lines are traditional approaches based either just on the phylogeny or just on the traits. And you can see that those approaches work better than random chance, but not much. We have a high error rate, up to about half of the time we get the wrong answer with traditional approaches. And then on the bottom we have in the gray line ABC, and in the medium dashed line at the very bottom random forest. And random forest can identify the correct model almost all the time, as long as the sample size is high enough. If you're an empirical ecologist, you might be a little bit dismayed by how big local communities have to be to make this work. I share that dismay. It is what it is. But I'll show you another method later that's a little bit more powerful in detecting these differences for small communities. We can also estimate model parameters pretty well. I'm just going to skip through this slide because I'm a little short on time. But these are sort of true versus estimated estimates of the strength of environmental filtering and competition in our models. And there's a little bit of bias and some problems with very strong selection that we can for exactly the right answer. But in general, the true and estimated parameters are related to one another. So I was pretty excited about that result. And I was actually really shocked at how well something as stupid as random forests worked. Sorry, I don't mean stupid like you're stupid if you use it. I just mean like what the computer is doing is stupid. But it works really, really well. One of the things that is a drawback of these kind of approaches is it's very difficult to figure out exactly what it is that the machine learning technique is using to give you the right answer. Am I really that close to the end? Yes. Okay, so the next approach takes this model down one level from species level to individual level. This is the work of Isaac Overcast, who's a postdoc in Helen Morlon's lab in Paris. It's called MESS, the Massive Eco-Evolutionary Synthesis Simulation, which is a great acronym. Isaac's model differs from Megan's because it works on the individual level. Their individual organisms are dispersing into the local communities. Otherwise, it's exactly the same. But the key thing that happens when you transition from species to individuals is you get new and different types of data. So individuals, for example, have abundance distributions. And abundance distributions have always been used by ecologists to try to understand community level processes. Individuals also have genes that mutate. And so Isaac has figured out a way to calculate test statistics from population genetic data that can be applied to these questions. And what we learned from that actually is that there is a signal of the generating process in the union of the phylogeny, the population genetic data, and the species abundance distributions. These plots are too busy to talk about in the 30 seconds that I have for this slide, but trust me when I say that if we look at either the abundance distribution on the left, patterns of genetic diversity in the middle, or patterns of species trait values, we can see differences in the assembly process that governs how communities come together. And basically, in the framework of the symposium, we can see the imprint of species interactions in all 3 of these areas. One interesting observation, actually, is that species interactions and habitat filtering both imprint the population genetic data in a really similar way instead of a really different way. So we can tell that this model is not neutral, basically because species rapidly expand their population size because they fit well in the environment, either biotically or abiotically, and it leaves the same imprint in population genetic patterns. It's kind of neat, right? This model works much better. So we were sort of comparing what happens if you have the traits or the abundances or nothing, but the top left corner is the only thing you need to look at here. That's the power of this model and its misclassification rates versus local community size, but here it's number of individuals, not number of species. And so even with a few species, but sampling a lot of individuals and measuring population genetic data, species abundance distributions, and phylogenies, you can really clearly differentiate among these models. Okay, so conclusions. Sorry, I know everyone wants to go on their coffee break. So simulations and machine learning provide a powerful new tool to combine ecological and evolutionary inferences. And to me, this is really surprising how well this works. And it's, in particular, information is contained in the interactive relationship between ecological and evolutionary measurements. And I think this is a good example of why we should enjoy our time as the last generation of human scientists. I don't think that we have any time for questions, do we? No. Okay, so just find me and ask me questions if you have them. Thank you for coming.